Hi. So if you've been struggling with the merge sort algorithm, I'm going to try here and give you a very visual explanation of how it works and then how we implement it using recursion in Python. So let's get started. So for the merge sort algorithm, there's basically a few foundational ideas that it uses. The first one is that single element lists or arrays, and I use those terms interchangeably, but in Python we'll be using lists, but arrays in general. Single element arrays are already sorted. So if you have an array that contains just the element 9, well, that array is sorted. And it can contain any number, -1, 0, 3.14. If those are single element arrays, they are already sorted. And that's key to the recursion principles that we're going to use with the merge sort algorithm. And then we also have an algorithm that will merge two already sorted lists into a single sorted list. So this is, again, kind of the basis of the merge sort. It's this merging concept where we take two already sorted arrays, and that's key. The arrays have to be sorted already. And then there's an easy way that we can then use to combine those two sorted arrays into a single sorted array. And then we're going to use a divide and conquer approach with the merge sort algorithm. And we're going to implement this divide and conquer algorithm in Python using recursion. All right, so now let's take a look. The single element array being sorted already, that's kind of trivial. That's easy to understand. So let's see now the algorithm that we're going to devise to merge two sorted arrays together. All right, so let's start with just two arrays of size 1, like so. And let's get them so that... All right, so if we start with these two arrays, 8 and 7, and these are two sorted arrays because they are single element arrays, right? Now, how do we combine these two arrays into a single two-element array that is sorted? Well, what we do is we basically compare the elements, the first element that we're looking at in each array, right? So we look at the first element here in this array, which is 8. We look at the first element in this array here, which is 7. We compare them. The smallest one is the one we're going to take first. So in this case, it's going to be 7. We're going to take 7. Now, there's no more elements in this array here. So basically, since this is already a sorted array, we know that we can just grab all the elements from that array and append them to our result. In this case, there's only one. So when we are done, we now have 7, 8, which is a two-element array with sorted elements. And here I'm sorting in ascending order. All right, let's make it a little bit more complicated. Let's do two elements here, and let's do this one. So we have 4, 9, and 3. So we have one array which has two elements, which are sorted, and then we have the second array, which has one element, which is, of course, also sorted. So we do the same thing. We start with 4 here and 3 here. We compare the two numbers, and we see, well, which one is smaller? Well, 3 happens to be smaller. So we grab 3. And we're done with this array over here. Anything that's remaining now is already in sorted order, so we can just grab those as is, one by one, 4 and then 9. And then we're done, and we have an array 3, 4, 9. Let's make it a little bit more complicated. Let's go with, let's say, 3 elements and 3 elements. So we have this over here that we want to then merge. So let's note the left side array 7, 10, 12 is sorted. The right array 5, 7, 11 is also sorted. And now we want to merge those two things together. Well, again, we just keep track of the element that we're looking at in each array. So we start off by looking at the first element of each array. We have 7 and 5, which is the smallest one, 5. So we grab 5, and that goes into our result. Now you'll notice that 5 is now done, so it's grayed out, and now our pointer is saying the next element that we'll be looking at is going to be 7. And this one here, the pointer is still pointing to the first element. So now we do another comparison. We compare 7 to 7. Here, they're both equal, so it doesn't matter which one we take. We take one of them, so we'll take one from the left array, and we move our pointer now to this second element, 10. And we repeat. We again do the comparison now between 10 and 7. 7 is smaller, so we're going to grab 7. and our pointer moves to 11. So we're just keeping track of which items we've already handled in those arrays. So now we do another comparison, 10 and 11. Well, 10 is smaller, so we grab 10. Now we do another comparison, 11 and 12. 11 is smaller, so we grab 11. And then we do the same thing with 12. And we're done. Okay, so this is the basic concept of merging two already sorted arrays. All right, so let's go ahead and implement that in Python. All right, so we're going to call this merge. So I'm going to call the function merge. It's going to take two arrays or two lists, L1 and L2. Now remember, L1 and L2 are already sorted. L1 and L2 are already sorted. That's the key thing. We're just merging sorted arrays here. So we're going to have to keep track of the indexes, right, that I showed you just now. We were keeping track of indexes for the left and right arrays. So we're going to use I and j as those indicators. And of course, we start with element index 0 for both arrays. Now, we're going to repeat this loop as long as we haven't finished looking at all the elements of at least one array. So as long as we still have elements to look at in both arrays, because remember, we're doing those two comparisons every time. But as we saw, when one array kind of emptied out before the other, then we kind of switched what we did. We just grabbed all the remaining elements from the one array that still had elements left that we hadn't handled and just added them to our result. So we're going to do the same thing here. So as long as we have elements to look at in both arrays, so while I is less than length of 1 and j is less than length of L2, this should be L1, like so, then what are we going to do? Well, we're going to compare. We're going to say if L1 I is less than, and we'll do an equal sign as well. So as we saw in the algorithm that we had, where I was showing you visually what was happening, if we had equal elements, I took one from the left. It doesn't matter. You could take it from the left or the right. Here I'm going to take it from the left. So if L1, if the element we're looking at in the L1 array is less than or equal to the element in L2 array, so L2, now remember we're using j to see which position we're at in L2. If that's the case, then we're going to take our result and we're going to append that value L1 to our result. Now, result is not defined yet, so I need to go ahead and define an empty array. So we are creating more space, right? We need space to store this thing. So we have these two arrays, these two lists, L1 and L2, and we're going to be creating a new list that's going to contain the same number of elements as L1 plus L2. So we're kind of doubling up the amount of space that we're using. And this is something I'll discuss later when I talk about the space complexity of this algorithm. All right, so we append L1I to our result, and of course we have to increment I. We've now finished handling element I. We're starting off at 0, let's say. Now we're looking at, the next round we'll be looking at element index 1. Okay, so this is exactly what was happening in that visual demonstration. Now, if that was not the case, this means that the element in L2 was less than L1. So what are we going to do? Well, we're going to grab the element from L2 instead. So we'll take L2j, and we're going to append that to the result. And then we have to increment j, like so. Now, once we come out of this loop, this means that we've finished handling all the elements in at least one of the arrays. So one of the arrays is now, you can think of it as empty, right? We've handled everything. So the other array could be empty as well, or it could have something in it. So technically, we should find the non-empty array that's left. There will always be one empty array in here, because this is guaranteeing that we finish this when one array empties out. Now, maybe both empty out at the same time, but at least one did. So which array are we going to grab all the remaining elements from? Well, it doesn't matter. We could test and say, well, if the length of, if I is less than the length of L1, then that's the non-empty array. But we're not going to do that. We're simply going to take the remaining elements in L1 and add it in, and take the remaining elements in L2 and add it in. Since one of them is going to be empty, it doesn't matter, right? So we don't have to check. So we're going to use Python's extend. Remember, we can use the extend. And what are we going to do? Well, we're going to look at the slice of L1 starting at I, right? Because this is where our indicator, our pointer is, I. So again, just go back to the simulation if you're not understanding this correctly. But we're basically taking the remaining elements from L1. Maybe L1's empty, but if that's the case, then this will do nothing. And then we're going to do the same thing, but this time with L2. So we'll take L2, J, forward. And again, if there were elements left in L2, it will grab all of those and just append it to our result array. If that one was empty as well, then nothing will happen. And then we just have to return our result. That's it. That's our merged array. So let's take a look at how it works. Let's say we have merge, and let's say we're going to merge 1, 3. Remember, the arrays have to be sorted, right? And then 2, 4, like so, right? So both of these arrays are sorted. When we run this, we get the merged array, which is now also sorted, 1, 2, 3, 4. And you could do this with an odd number of elements as well, or unbalanced 2, 4, 6, 8, for example. You could do that. We still end up with the merged sorted array 1, 2, 3, 4, 5, 6, 8 in this case. All right, so these are the two fundamental concepts of the merge sort. The one is single element arrays are already sorted, and the second one is if we have two sorted arrays, we know how to merge them together into a single sorted array. So now let's look at the divide and conquer approach that merge sort algorithm uses. Okay, so let's say that we want to sort the array 2 and 1, like so, right? So this is a 2-element array. It's not sorted, as you can see, and I want to sort it. What do I need to do? Well, the first step is I'm going to split this array in half. And in general, it's roughly half. You'll see why when we have an odd number of elements, you can't split exactly in half, but that's okay. So here we'll start with an even number of elements in the array, and we want to sort that. Well, remember, we know how to sort single element arrays because they're already sorted. Now this is not sorted. So the first thing that we're going to do is going to split that in half. So we split those into two arrays. The two element of the array with a single element 2 and an array with a single element 1. So now we have this split. And now we have two arrays that are sorted. So what can we do? Well, now we can actually merge them. We can merge these two single element arrays. We already have our merge algorithm done. So all we do is we grab 1 from 1, 2 from the first one, and we're done. That's it. We've sorted the array 2, 1. Now we're at 1, 2. All right, so let's make that just a little bit more interesting. Let's say we have 3, 5, and then 6 and 1, let's say. And we want to sort that. So we're starting with this array. What do? We divide. We split it in half. So that's the first thing we do. So we get the array 3, 5 and the array 6, 1, or lists if you want to talk about Python specifically in this case, as I'll be implementing it using lists. But I'll refer to it as arrays in general. So we have 3, 5, and 6, 1. Is 3, 5 sorted? No, 6, 1 wasn't sorted either. Now it could be that 3, 5 happened to be sorted, but we don't know that. We just split it. So this is a 2-element array. We can't do anything yet with that. So what do? We split 3 and 5 into 2 single-element arrays. And in the next step, we can now merge those two because 3 and 5 are single-element arrays. So they're both sorted arrays, so we can apply our merge. So when we do that, we merge 3, we merge 5. And we've essentially sorted 3, 5. It is now the 3, 5 over here. The next step is to look at 6, 1. We need to sort 6, 1 as well. So when we do that, we split that into 6 and 1. Those are both single element arrays. We can merge them. And when we merge them, we get 1 and 6. So now you can see what happened, right? We started with 3, 5, 6, 1. We split it in half. That wasn't enough. We split it in half again. We then end up with a sorted left array now, 3, 5, and a sorted right array, 1, 6. Well, what's the next step? Since these are two sorted arrays, we can merge them. And so here we go. We're going to merge them. So we're going to grab 1, then 3, then 5, then 6. And we're done. We've just sorted this array over here. And that's the merge sort algorithm. It's actually really, really simple when you break it down this way. So the key is that we divide the arrays in half until we reach single element arrays that we can then merge back together. And then, so we end up with this kind of stack of split, 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 and then we start merging back up towards the top. So let's do another one. Let's do 8 and 6 and maybe 5 and then 3 and then 9 and then 9. Let's do 2. So here we have 1, 2, 3, 4, 5, 6. Let's do 5. Let's do 5 just to show you what happens when you have an unbalanced and uneven number of elements in there. So first thing we do is we split. Now we can't split exactly in half, right? Because we have an odd number of elements. So in this case here, I'm taking the first 2 elements and then the last 3 elements. So your splits are always going to end up this way. Either you take 3 elements here and 2 elements here, or 2 elements here and 3 elements there. Then that's fine. That's not a big deal. So now what do we want to do? Well, in order to get to this one sorted, we need to first sort those 2 sub-arrays, those 2 divided arrays. So we do that. Now, how do we sort it? We can't sort a 2-element array, so we split it again. Now we end up with 8 and 6. Those are single elements. They're sorted. We can now merge them. So we merge them back into 6 and 8. All right, so we've sorted the left side of the split. Now, before we can merge those 2 back into the main one, we need to also sort 5, 3, 9. So again, 3-element array, we need to split it. So again, we split it. And again, we have an uneven split, right? So we have 5 in the 1 and then 3 and 9. Well, we can't merge those yet because we need to sort each one. Now, 5 is already sorted, right? But 3 and 9 is not. So we need to split 3 and 9 again. And this is that recursive call, right? That divide and conquer that I was talking about. We were splitting, splitting, splitting until we reach single element arrays. Now, those 2 arrays are sorted and we can merge them. So we merge them, 3 and 9. What's the next step? Well, we now have to merge 5 and then this sorted 3, 9 array, which was 3, 9. So we go ahead and merge them. So we get 3, then 5, then 9. So now you can see we're kind of walking our way backwards, right? We split 8, 6, 5, 3, 9 into 8, 6 and 5, 3, 9. We now have sorted both of these, 6, 8 and 3, 5, 9. And so the final step remains now of merging these 2 sorted arrays. And so we're going to merge them into 3, 5, 6, 8, and 9. And we're done. We've merged. Now, of course, as you can imagine, this can get more complex, right? So we could have, let's say, a 9-element array. Let's go ahead and... Oh, I can... All right, for some reason, I think my code a little bit messed up, maybe. There we go. So we could go with 9, right? So it's just going to be a lot of more steps, right? So let's go ahead and work through it. So we split in half, approximately half. Then we split that in half again. We still need to split because we haven't ended up with single element arrays yet. We split again. Now these 2 are single element arrays we can merge. So we merge them, we get 11 and 13. Now we move on to the 8 and 4. We have to split that. Now we can merge them. So now we get to 4 and 8. Now 11 and 13, 4 and 8 are sorted arrays. Well, we can merge those 2 back together. So we get 4, 8, 11, and 13. So now, as you can see, we've sorted that first split that we had over here, right? That very first split is now sorted. Now we have to go on to the second side. So we have to split that. Again, we keep splitting until we get to single element arrays, which are sorted. And now we recombine them. 6, 11. And now the 1, 17, 3 we have to sort. So that gets split into 2 subarrays. 17 and 3 still need to get split. So now we have those 2. we can now merge them because they are already sorted single element arrays. So we get 3 and 17. Now we have to merge 1 with 3 and 17. 1 is already sorted, so we don't have any more processing there to do. But now we can merge those back together. So we get 1, 3, and 17. Now we've got 6 and 11. This 11, 6 is sorted now as 6, 11. The 1, 17, 3 is sorted as 1, 3, 17. And we have to merge those two. So when we merge them, we get 1, 3, 6, 11, and 17. So now we end up with our two initial subarrays, right, that are now sorted. And the final step then is to, again, just merge those. So when we merge those, we get 1, then 3, then 4, then we're going to get 6, then 8, then we have 11 on both sides, so we'll take one of them, doesn't matter which. Now we have 13 and 11, so now we have the 11 from the other one, so we'll grab that one, then 13, then 17, and we're done. And that's the merge sort algorithm. We keep splitting our arrays until we get to single element arrays because those are sorted. We know they're sorted. And then we apply this merge algorithm for sorted arrays that we already have developed. Now, the way I'm showing you here is kind of the way that the third process is. But in terms of a recursive call, that's not exactly what's happening. Right here, it looks like I'm outputting new rows every time. Because we're using recursion, we're going to have a call stack where we're going to split, 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 split. And then the merge is going to kind of roll back that stack up. So let's take a look at what that looks like. So let's start simple. Let's do this 2, 5, 6, and 7. And actually, I want to change it so it's a little bit more unsorted. So 5, 3, 6, and 1, let's say. Okay. So let's start with this. So the first step is we split, right? So we have 5, 3, and 6, 1. Those are the two splits. We need to sort those before we can merge them. So we, again, send them to the same sort function. What does the sort function do? It splits and then tries to merge the sorted arrays, right? So now we have to split. So again, we split 5 and 3. Well, that now is in sort, that those are two sorted arrays, right? So what do? Well, we're going to merge 5 and 3 now, but we're going to merge it back as a return value, as a return from saying merge 5 and 3. It's going to come back, right? So what happens is that we replace the original array with the result of this merge, 3 and 5. So this is us unwinding the call stack. It will make more sense when I show you the code, but that's essentially what's happening. All right, so now we've sorted the first split, 3, 5. Now we have to sort 6, 1 before we can merge it, right? So how do we sort 6, 1? Well, again, we split it into two arrays, 6 and 1. Those are sorted. So now we can merge. And so the 1 is going to go back as the first element and 6 is going to go back as the second element. So it's going to come back as a sorted array. And now we have these two sorted subarrays. So originally they were unsorted. Now they're sorted. And now we can merge them. And we merge them back into the original. So we get 1, then 3, then 5, then 6. And it works the same way even, if you have multiple levels. So I can show you, let's say we have 7. So we'll work this way. We split. Here we have to split. Now we can merge back. So we merge back this way. And now we can merge those two back because 14 is already sorted. 2 and 11 has just been sorted. So we merge them back. So we get 2, 11, 14. Then this one, again, we have to sort. So we split that. Each of them is a 2-element array. So we need to, again, further split them. Now we have 4 and 12. Well, we can now merge those two. So we get 4 and 12. Here we have 14 and 14. They're both single element arrays. They're already sorted. We can merge them. So we merge 14, 14. But now we still have to go back and merge those two sorted arrays. We're not done yet. So we have to merge those two together. So when we do that, we get 4, then 12, then 14, then 14. And now that we're done with that, now we have to merge those two. And so when we merge them, we get 2, then 4, then 11, then 12, then 14, then 14, then 14. okay? And so we end up with that sorted array. So that is the merge sort algorithm. The key thing, a single element array is sorted. We know how to merge sorted arrays, and we use this divide and conquer approach where we essentially keep dividing our unsorted arrays into halves and then sort the halves. Now, how do we sort the halves? Well, by, unless they're single element arrays, how do we sort the halves? Well, we split them again into half, and then we keep doing this until we end up with single element arrays that we can merge back together and walk this back up our call stack. All right, so let's go and actually do that in Python. It's very straightforward now that we understand this, and now that we understand this recursive approach. All right, so let's go ahead and write this sort function. So we're going to sort some list L. And I'm going to write this out kind of verbose, and I'll simplify it later so we have a more compact Python function. But for now, just to understand exactly what's going on. Well, the first thing is, how do we sort a list that contains a single element? Well, we don't have to. It's already sorted. So that's what we're going to check. We're going to say if the length of L is less than or equal to 1, then we're going to return the list itself because it's already sorted. Now, why do I say less than or equal to 1? Well, I just want to trap the case where somebody sends in an empty array, right? So if you send in an empty array, I don't want this function to crash. I just want it to return the empty array because trivially that's sorted as well. Just like a one element array is already sorted as well. And this is key because this is what is going to, in our recursion, give us that exit condition where we stop the infinite recursion. But let's continue. So now we have a list that is more than one element. So what are we going to do? Well, we're going to calculate a midpoint, and we're going to say this is the length of L divided by 2. So this is an integer division. Now, of course, it's the approximate midpoint. If it's an odd number of elements, it's not going to be, we're not going to cut our array exactly in half. One array will have one more element than the other. Which one has one more? Doesn't matter. Pick, doesn't matter. Here, I'm going to just take this midpoint, and I'm going to call left, and I'm going to take my array L, and I'm going to start at 0 and go up to midpoint, like so. And then for my right array, I'm going to take L, and I'm going to start at midpoint and go all the way to the end, right? So now I've split this array into roughly 2 equal parts. Now, I need to sort those before I can merge them, right? Because I can only merge sorted arrays. So how am I going to sort them? Well, I'm writing a sort function right now. So this is what's sometimes called the leap of faith when you're writing recursive functions. And basically you're saying, well, I'm writing a sort function. I'm going to, assume that I'm writing it correctly. And so I should be able to use that function to sort anything within that function itself, right? That's recursion. And so it makes this assumption that the sort function is written correctly. If it's not, everything's going to blow up, and then you have to go back and debug. But if it's working correctly, well, I can really just say left sorted equals, and we're going to sort the left array, right? I'm writing a sort function. Well, I'm going to use it. And I'm going to do the same thing with right sorted. I'm going to say sort right, like so. So now I have 2 sorted arrays. I've got the left, I split it, I sorted each one, now I just need to merge them. Well, we already have the merge function over here, right? We just defined it. So let's go ahead and say result equals merge left sorted and right sorted, like so. And then we're just going to return the result. Okay, and that's the sort function. If I've done everything correctly, it will work just fine. Let's go ahead and try it. Let's say sort, and we'll sort, let's say 8, 5, 3, 6, let's say, like so. Okay, we'll do 4 elements. Let's see what we get. Midpoint is not defined. Because I called it midpoint like that here. Let me try again. Okay, and as you can see, it sorted it just fine. 3, 5, 6, 8. Now we could try different ones. We could say sort 8, 5, 6, 8, 10, 3, -1, 0, 9. It doesn't matter, right? It's all going to work perfectly fine. -1, 0, 3, 3, 5, 6, 8, 9, 10. That is the merge sort algorithm. So we are using recursion here, right? We're using a recursive approach to this. It's this divide and conquer that I talked about. And then we're using this merge. This key function here is this merge that we really count on for merging sorted arrays. And then the other key is this one over here, that a single element array is already sorted. And this is what stops the recursion, because when I reach finally, a left and a right, if I say sort left and it only has one element, well, the sort function is just going to return it. It's not going to keep, digging down into the depths of the recursion, doing more and more calls. All right, so before I finish up this video, one last thing I just want to talk about, if you're interested in that. Otherwise, thanks for watching and goodbye. But I'm just going to briefly talk about the complexity of this algorithm. Oh, before I do that, let me just again talk about this recursive algorithm, because that I know can be a little difficult to wrap your head around if you're not used to recursion. So if we have this function sort L, what are we going to do? Well, we're going to check to see if the length is 1, right? If it is, just return it as is. We're also taking into account the fact that you could pass in an empty array. So we check to see if it's less than or equal to 1. So this is what stops this infinite recursion problem. So if it's not, though, if it's greater than 1, then we split it into 2 halves, left and right. And they're approximate halves, right? And then we call sort on the left and sort on the right. That's the recursion. This is that leap of faith recursive call. Then we obtain the left sorted and right sorted splits, right? Which could have gone into multiple splits, right? As we saw in the animation, it could go down multiple depths before it started merging back things into the final result. And so we now have the left sorted and the right sorted, which we can merge. And we just return that result. All right, so that's the basic merge sort algorithm. And we implemented it using recursion in Python. Now, in terms of complexity, the merge sort algorithm is an interesting one because it's very predictable. Because the best case, worst case, and average case is all the same complexity. It's O(n) log n. And this is because when we do, and I'm not going to explain complexity. If you don't know complexity and you're interested, you'll need to go and learn about that somewhere else. If you're not interested, just skip this. This is totally irrelevant, other than saying it's a pretty good sort algorithm, right? It's actually a very good sort algorithm. So the reason we get n log n is because, well, we're doing this binary. It's like a binary search, right? We're splitting this array into half, 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 half. Essentially. So this gives us an order log n, an O log n. Now at each level, we perform comparisons. We perform n comparisons, right? To get the elements back to merge the elements back. Remember, we had to compare each element from the arrays until we reach the end, right? So the complexity there is O(n). So that's why we get complexity total is n log n. Now, in terms of space complexity, you'll see very often in textbooks that the complexity is O(n). And yes, the algorithm can be written that way. But the algorithm we wrote here, using recursion and using Python, and doing the splits, and doing, splitting the 2 arrays and having that left split, right split, right, all that essentially isn't very ideal in terms of space complexity. We're creating more things than we have to. So in fact, and our implementation that we just did is actually n log n as well for space complexity. Okay, but you can make it O(n) in theory and in practice as well. I'm just not doing it here because it's going to muddy the waters in terms of understanding the algorithm, but it can be done. And this is because we're splitting arrays in Python, which creates new arrays. So we've got copies of the data that we don't technically need, and so on. And because we've got a call stack using recursion, that memory persists, right? As we're splitting the arrays, every time we're maintaining these copies of copies, right? It's just subdivided each time. All right, so now one final thing. I told you that I would clean up that Python code just to show you that I wrote it kind of, verbose, and we can make it a little shorter. So let's just switch to that quickly and see. So this is our sort algorithm. So what we can do, let me redefine it, say def sort L. And we're going to do the same thing as before. If length of L is less than or equal to 1, we're going to return L. That doesn't change. We still need that. But then what do we want to do? Well, we need to calculate the midpoint. So I'm just going to copy paste that. So we still need that midpoint. And the reason I'm putting it into a variable is I need it twice. So we need that. And I'm just going to say return, merge, sort. And we'll take L. Remember this one, L to the midpoint. And sort right to midpoint. Or I should say the right array, right? And that's it. So you can write the sort this way as a recursive function in just, 4 lines, essentially. So if we can just test it out, we'll see that we should get the same result. All right. And as you see, we get the same sorted result. All right. That's the merge sort algorithm. Thanks for watching and see you next time.